So today's topic, we're going to be talking about beam bending. And so a lot of this should be reviewed for you. Yeah, so a lot of this will be review. So we'll just kind of go through it. But some of the derivations might be a little bit more in depth compared to what you've seen before, that's all. So essentially, if we start off by considering a sliver of a beam along its length, right? So the x direction is along the length of the beam. And we have a load that we're just representing as a generic distributed load for now. Then if we consider the internal forces on either side of that sliver, right, there's going to be a change from the left side to the right side across that small distance. And that change is due to the load that's present on that length of the beam, right? So basic equilibrium analysis, if we sum forces in y, right, we get dv dx is equal to negative q. And if we sum forces, or sum moments, about the center or the origin of those axes that we noted there, then we get dm dx is equal to v. So combining these, we can get the second derivative of moment directly related to the distributed load. So now if we consider strain displacement, with the assumption that plane sections remain plane, here we have, so just to make this a little more clear, all right, there's our beam segment that's bent now, all right, under some bending moment, maybe due to the transverse load, for example. And if we measure from the center of curvature to the neutral axis, we call that distance rho. Then we could consider within the depth of the beam a measurement variable distance y, right? And we start that measurement from the neutral axis. So I'll note down here, and then we'll write some stuff over on the right side in a moment too. Y is measured from the neutral axis. Towards the center. And then this is also assuming that the beam cross-section is symmetric about the y-axis. So later on, I think next week maybe, we get into, or no, it's not next week, I think in a couple weeks, we get into some other considerations like asymmetric cross sections or skewed loads and things like that. So right now we're just keeping it simple with symmetric cross sections and transverse loads that are not skewed with respect to the YZ cross section plane. All right, so I got that covered. All right, so now this length, all right, so as that beam bends, right, the outer fibers will shorten or lengthen depending on where they are with respect to the neutral axis, right? But this distance here at the neutral axis will not change length. So we can write that as rho delta theta. And define rho as the local radius of curvature measured to the neutral axis. So the normal strain in the x direction, which would be the longitudinal strain, represents the axial strain from bending. And we can write this as the change in length divided by the original length, right? So if you're at some arbitrary location within the cross-section measured from the neutral axis, let's say this point right here, we'd write that as rho minus y times delta theta minus delta s divided by the original length, which is delta s. And since we just defined delta S as rho delta theta, this simplifies to negative y over rho. So then we'll introduce another Greek letter, kappa, lowercase. And that is a symbol that we use to represent the curvature, which is defined as 1 divided by rho, the radius of curvature. And this is also equal to the second derivative of the vertical deflection or transverse deflection with respect to x divided by in brackets 1 plus dv dx squared, and then that quantity to the 3/2 power. Does anybody recognize that from mechanics of materials? Depending on who taught it, you may or may not have seen it. But I know when I taught it, I included it in the notes, and then I said, we brushed by this, and we're doing the same thing here, right? So we can approximate this as the second derivative of the deflection with respect to x. And the reason for that is because this denominator we can simplify to 1, right? Because this term dv dx is really small. And so when you square that and then take a power of that, it just is essentially going to be 1. So all right, and so then over here, I will also define, I verbally said it, but we didn't define it anywhere yet. So lowercase v represents the transverse beam deflection. So I usually write my lowercase v's with a tail on it or something to distinguish it from capital V for shear, because it's easy to get those confused in notes and homeworks and things like that. So, and exams. So whatever you do, find a way to distinguish the two, and that way we can all be on the same page. All right, so what this brings us to is an expression for normal strain in the x direction. All right, so that's equal to negative y times the second derivative of v with respect to x. All right, so that's just saying y over rho with replacing this for 1 over rho. So now we have derived the relationship of strain to curvature, right? If we apply our constitutive relationships now, we can relate stress to y and rho as well. So in this scenario, right, because we have a beam in bending, the only significant strain is that normal strain in the x direction. Are there other strains present? Technically, yes, but they're not significant for our considerations. So in this case, we'll just consider normal strain in x. And so that way we don't have to relate, we don't have to bring Poisson's ratio into play, is what I'm getting at. Right? We can just straight up say normal stress in x is equal to Young's modulus times strain in x, or sigma x is equal to negative y times Young's modulus over rho. So this tells us then that stress varies linearly with y, because remember that y is a variable distance measured from the neutral axis. And you can see that on the image to the left, where you have the normal stress distribution sketched across the y direction of the cross section here, where it's 0 at the neutral axis and then increasing in magnitude towards the extreme fibers. And then depending on how it's being bent, right? So for a positive moment, as shown here, you would have compression above the neutral axis and tension below the neutral axis. All of that is stuff that we already know. And so what this is bringing us to, right, we're ultimately getting to a derivation of other relationships between moment, stress, strain, etc., and loads. So because there is no net axial force for pure bending, right, because they balance out above and below the neutral axis, we can make use of that in our manipulations of the math, right? So that means we can say, if we integrate over the cross-sectional area, the normal stress, we would get 0, right? No net axial force. So making our substitution, right, of sigma is equal to negative y times capital E over rho, we can bring Young's modulus and rho in front of the integral, because with regard to a specific location along the length, rho is constant, right? It doesn't vary with y, and Young's modulus, of course, won't vary with y. So we can treat those as constants, and then we're just left with y dA inside the integral. And so that leads us to the conclusion that the integral of y over the area must be equal to 0. So this is the proof, if you will, that the neutral axis is located at the centroid of the cross-section. And since both x and z also pass through the centroid, they are also neutral axes. Or I guess the way I wrote this, it makes more sense to say they are both neutral axes. And y is neutral axis as well. We're just not considering bending about y. Although later on we will. All right, so now we can relate the moment and bring that into play. So moment is equal to negative integral over the area of y times the normal stress. All right, so that's just taking integral of normal stress over the area gives you the force, and then y gives you the moment arm. And then making our substitutions, we would get E over rho times the integral of y squared dA. And you may recognize this term as the moment of inertia, about z. All right, so this expression becomes EIZ over rho for a moment. And so below we have the resulting of additional forms relating moment to curvature. Right, and then relating stress and moment. And then relating the deflection directly to the loading. So just using what we just derived here in combination with the relationships we defined on the previous page, we can get all three of these equations. Any questions so far? Okay. So next page then, we'll talk a little bit more about beam deflection. And these methods should be familiar from mechanics of materials. Starting with the moment equation, right, and then integrating twice to get your deflection equation, or starting from an expression for the applied loading, Q, you can integrate 4 times to get the expression for deflection, right? Does that ring a bell? A painful one? Painful memories, maybe. A lot of calculus there. And so we'll just do a quick recap, right? If you consider this cantilever beam with a point load at the end, taking a cut of that beam, right? Draw a free body diagram of what you exposed. Or I guess you could technically take either side of that cut, right? But it's easiest to take the right side. So you expose the internal shear and the internal moment. We're not concerned with the shear for this particular example here. And then another important piece is just the length of that segment, which would be L minus X. And then you just sum the moments about the cut to get your expression for moment along the length of the beam, which is going to be negative P times L minus X. Right, and as a quick gut check, we can see that expression represents a linear relationship with moment along the length, and that makes sense because with a point load here, your beam shear diagram will be constant and your moment diagram will be linear, right? So then taking that moment expression and relating it to the deflection or the curvature using this guy up here. Applying 2 integrations. I'm not going to go through the calculus. I'll just give you the result. You get EI times the deflection is equal to PX cubed over 6 minus PLX squared over 2 plus a constant C1 times X plus a constant C2. In order to find those 2 constants, as you may recall, we need to apply boundary conditions. Who remembers where we get those boundary conditions?
Yeah. There's zero deflection at the
Yeah, so we look at the supports, right? Because that'll tell us where we have zero deflection. And sometimes we have to use in this case, we don't have to use the free end, but sometimes you might need to use a free end. And in that case, the condition that you know, the thing that you know would be the applied loading, right? But a lot of times we can get away with just using supports and using that in this case for the deflection and for the slope. So we need two boundary conditions to solve for those two constants. So at x equals 0, we know that the deflection is equal to 0, and the slope, which is dv dx, is also equal to 0. So then applying those boundary conditions, you can solve for C1 and C2 to get the complete expression for beam deflection along its length. All right, so that's starting from the moment equation. But sometimes it's actually more convenient, easier, better to start with the load expression and actually integrate twice using the fourth order derivation. Sometimes that's better because your moment expression might not be as nice and simple as this. If you have a really complicated moment expression, it can be, hard. It can be more work than you want it to be to get that expression using statics and then start the derivation from there. So if you want to start with the load expression instead, usually it's best to start with the easiest one, right? So in this case, we would have EI times the fourth derivative of v with respect to x is equal to negative q. All right, and so if we integrate that expression once, we would get an expression for shear. And then if we integrate it twice, we would get our moment expression. The third integration gives us deflection, and the fourth integration will give us, the third integration will give us slope, and the fourth integration will give us deflection, right? All right, so in this case, q is a constant, right? So we can clarify that by saying q of x is equal to just negative q. So after 4 integrations, we would get our expression for deflection, and that would be negative qx to the fourth over 24 plus constant c1 x cubed over 6 plus constant c2 x squared over 2 plus constant c3 times x plus C4. So now we need 4 boundary conditions, and this is where we have to consider the free end. So we can use the same 2 that we had before, since this is a cantilever beam with the same configuration. So at x equals but actually we'll do those later. So the reason for that is because the order in which these constants come, right? So We picked up C1 with that first integration, which I said gives you shear. We picked up C2 with the second integration, which gives us moment. So that is an indication that with these conditions, these boundary conditions, we'll be able to solve for our constant C1 with the shear boundary condition, right? So we get our shear and moment boundary conditions from the free end. So at x equals L, our capital V, shear, is equal to 0. So the third derivative of V, little v, right? Third derivative of little v with respect to x is equal to 0. That gives us our constant C1 being QL. And then also at x equals L, our moment is equal to 0. So that means the second derivative of v with respect to x is 0. And that gives us the value for C2, which would be negative QL squared over over 2. And then we go to the support and use those same two boundary conditions we had before. So at x equals 0, lowercase v is 0, and the slope is 0. So that would give us C4 is equal to 0 and C3 is equal to 0, respectively. So then we have the final result for that equation of deflection below. And these expressions, as some of you may already be familiar with and aware of, are often provided in tables in mechanics of materials books, structural analysis books, things like that. So I believe in this handout, towards the end, there is, yes, we have some of these provided for you. And I apologize that the quality isn't the best on these, but the reason I keep them in this handout rather than updating them to a newer set of tables is because I actually don't have the original source for this, and these 2 pages are more complete and comprehensive than most of the other tables that I've seen in textbooks. So I know it's kind of hard to read, but it gives you a lot more than what you might find elsewhere. And they're generally, pretty basic configurations, right? So you've got one page for cantilever beam and one page for simply supported beam. But you have various arrangements of loads and their placements with respect to the supports, etc. And it gives you, if we zoom in on this, it gives you the equation for deflection, the equation for slope, and sometimes it has to be broken up into 2 regions depending on the loading condition. So here you have one expression for this zone and a separate set of expressions for after the point load. And then you also, and here, yeah, so depending on the configuration, it might give you extra information, right? It might give you deflection at the center or at a specific point. And so these ones give you deflections at a specific point, right, and slope at a specific point. So these actually are very useful for the fundamentals of engineering exam, for those of you who have yet to take it. If you can get familiar with the version that's going to be provided to you by NCEAS, because you get a PDF, I believe. It used to be a book, but now it's all online. So you get a PDF, and you should have a couple pages that have stuff like this on it. If you get familiar with that and just understand how to use it, it can be a real time saver. So heads up there. We'll look at a superposition example next, and we'll use these tables, or we'll refer to the tables in that example. Let me find my spot. Here we go. All right, any questions so far? Okay, good deal. And it's not just useful for the FE exam, it's also useful for everyday applications as well. So it's just a matter of kind of remembering that you have that resource and getting used to using it. All right, so now we'll talk about superposition. Who remembers this topic from Mechanics of Materials? Maybe? No? Not really? Yeah? Okay, so it was probably something that you didn't spend a lot of time on, but was covered briefly. So we're going to use the beam tables for this. And the challenge is to find the central deflection of the beam. And so this is actually a pretty good example of the type of problem that might arise on the FE exam that you could use these beam tables for. I think this one looks, and this one actually looks like it would be, I'd have to look again at what's provided in the FE tables, but this one might be doable using the tables that you're provided by NCs. I'm not 100% sure about the half-span distributed load. That might be a little bit too far gone for the FE exam tables, but we'll look at it in this class, and then you'll be extra prepared. So the idea is that with elastic analyses, right, you can treat each load separately, complete the analysis for the individual loads one by one, and then combine the results to get the effect of all loads acting at the same time, right? So if we consider the first load being just the distributed load over half the beam, and then skip back to this configuration, the table where we had simply supported beams, all right? And we look through and find the load pattern that most closely represents what we're looking at. And so in this case, we do have the exact condition that we're looking at, a distributed load over the first half of the beam. And so scanning through this, we can find the formula for delta C, which is the deflection at the center. All right, so here A would be the right end, B would be the left end, so we have the slopes for those points. These are all defined up above, but again, I know it's not the best quality, so I'll point it out. So we pull that value, right, 5QL to the fourth over 768 EI. And then to avoid flipping back and forth, I'll just go through the other ones, calling out the values, and then we'll write them down. So then the next one, we have the load, the point load, right? And the point load is not at the center, so we would not want to use this one. It's off center. And then here you just need to plug in values for the A and B distances and use the formula, all right? So if A is greater than or equal to B, which is what we have in the problem statement, that point load is located at 3/4 of the way from the left end. So if we plug that in this case, let's see, the equation, you just plug in B, all right? So if you plug in 1/4 of L, then we would get 11 FL cubed over 768 EI, and I'll write those down when we get back. Yeah.
This one, the pin and roller are inverted from the page. Is it
Right.
Is that A and B to the distance of the roller? Is it always left to right? Is A always the pin side and B always the roller side?
That's a good question. So for the vertical deflection, it doesn't make a difference which one is pin and which one is roller. Yeah. But if there may be conditions where you do have to switch. All right. So yeah, I'll try and think of an example where you do have to think a little bit more carefully about what you're given and make some adjustments, and I'll come back on Friday with those examples. But yeah, in this case, it doesn't make a difference. Yeah. So Let's see. All right, so moving on. The moment then, we have a moment at, okay, so yeah, so here, right, our moment is applied at the right side. Here, it's applied on the left side. But again, because with respect to vertical considerations, everything is symmetric, it doesn't make a difference. And since we're interested in the deflection at the center, we can just use the same, we can use this even though our moment is actually over here, all right? So using those values, taking them back to our previous page, we'll write them down over here. So we had, from this one, the deflection in the center was 5 QL to the 4th over 768 EI. And then from this one, that formula would spit out 11 FL cubed over 768 EI. And then from the moment, we had M naught L squared over 16 EI. So then adding them together, we would have 5 QL to the 4th plus 11 FL cubed plus 48 M naught L squared all over 768 EI. So if you know values, of course, for Q, L, F, and M, and E and I, you could readily calculate the deflection at the center using this method. All right, so those of you who have taken the EPI exam, did you use this approach for any problems? Did anything like that come up when you took it? No?
I don't remember.
You know, okay, fair enough. And I mean, it may be that, you know, the EPI exam has changed significantly over the last couple years. It may be that it's not as likely that you'll see a problem like that. I know that's still a possibility, of course, but I don't know. When I took it, it was like, I remember using this. But that was completely different format and whatnot. So, but yeah, it's useful. All right, so down here we've got just our standard beam sign convection, standard beam deflection sign convention. All right, give me a couple days off and I lose my ability to speak properly here. So this is just for reference, all right? When we do these problems, this is the sign convention that we're going to use, but just as a heads up, next week we're going to get into beams on elastic foundation, and then things are going to be flipped. So we're not going to use the same beam sign convention for everything in this class, just for these traditional beam bending problems, right? All right. Any questions? All right, very good. So we just have a few minutes left. I think this is actually a really good stopping point though, because we finished talking about beam flexure, and then the next portion of these notes are beam shear. So we'll go into beam shear and cover that on Friday. And then after that is when we will get into beams on elastic foundation, which is a pretty interesting topic. So, yeah. Yes.
Did you post homework solutions after?
Yes. Yeah, I do.
Okay.
Yeah, I'll post solutions generally around the same time that I release grades or, yeah. So, yep. You're welcome. All right, very good. Well, have a great rest of your day.